So we'll first start with evaluation of the constant A. Okay. So we know that the number density rho, which is given by n a cube e to the power minus b c square, is isotropic in velocity space. It means that as rho depends on only on c, that is the velocity. So no matter in which direction we go up to a certain magnitude, in this case the certain magnitude is that the certain velocity in that velocity diagram, it will have the same value. That is, it will have this spherical symmetry. It means that if we draw in the velocity diagram, if we draw a sphere of radius c, okay, so in 3D you have to perceive it as a sphere, okay. So if we draw a sphere of radius c, so no matter in which direction we go, suppose in this direction we go up to a certain distance c, okay, certain distance c, then we'll reach the surface of the sphere, and at this point we'll find that the number density is rho is given by n a cube e to the power minus b c square. Now if we choose another direction, suppose in this direction we go up to the same magnitude, which is c, then we will reach this point, which is again will lie on the surface of this sphere, and over here also we will find that the number density will be rho equals to n a cube e to the power minus b c square. Similarly, at this point, as we go in this direction, we will reach up to the length of c in the velocity diagram, then we will reach the surface of the sphere, and over here we will find that the number density is rho is given by n a cube e to the power minus b c square, and it is same for all the directions. So it does not depend on direction, it does not have any preferential direction for the number density, okay. So now suppose so that's why we can say that it has a spherical symmetry, okay. Now suppose there are dnc number of molecules which have their velocities lying between c and c plus dc. So till now we have talked about talked in terms of velocity components. That is, we said that there are some molecules which had their velocities lying between x component of velocity lying between u and u plus du, y component of velocity lying between v and v plus dv. Now this is c is their actual velocity, okay. Like if you remember, c square was u square plus v square plus w square, like that, okay, actual velocity. So now suppose there are dnc number of molecules, c is subscript for this velocity c, which have their velocity, actual velocity lying between c and c plus dc. So how can we represent these dnc molecules in the velocity space? So earlier, if you remember, we considered dn molecules which had their velocity components lying between u and u plus du, v and v plus dv, and w and w plus dw, and they were represented as their velocity points in a cuboid of sides du, dv, dw. Similarly, now here we want to represent this dnc molecule in the velocity space, and how we can do that, okay. So obviously these dnc molecules will be represented as velocity points in the velocity space or the diagram, okay, and they will lie within a spherical shell of inner radius c and outer radius c plus dc, okay. So in the velocity diagram, okay, suppose we have this spherical shell, okay, concentric spherical shell, okay. So we have the inner sphere of radius c and this outer sphere, the bigger sphere of radius c plus dc, okay. So these dnc molecules will lie, which have their velocities lying between c and c plus dc. We'll find that they can be represented as velocity points, and we'll find that they will lie within this spherical shell, within this region, okay, within this dotted region. So as you can see, thickness of this sphere is thickness of the sphere is dc. Okay, now so what is the volume of this spherical shell? So what is the volume of the spherical shell? It is the surface area of the inner sphere. So we can write surface area of the inner sphere into the thickness. So surface area of the inner sphere will be 4 pi radius square of the radius, which is this the radius is c, so it is 4 pi c square into the thickness dc. Okay, so now we'll find the expression for this dnc, number of molecules. Okay, so what will be dnc? We'll try to express dnc in terms of the volume of the spherical shell and the number density. So it will be equal to volume of the spherical shell into number density at the or within the, suppose within the shell. Okay, why is it volume of the spherical shell and number density within the shell? So generally if we have mass, okay, so mass is volume into mass density. Here we are trying to find the number of molecules, so number will be volume into number density. Okay, so that's why dnc will be the number of molecules which are lying within this spherical shell, and we can find it by taking the product of the volume of the spherical shell and the number density within that shell, that is within, what is the number density within this region. Okay, and what is the number density over here? It is rho equals to n a cube e to the power minus b c square. Okay, so therefore we'll put the volume of the spherical shell, which is 4 pi c square dc, into number density within the shell, which is n a cube e to the power minus b c square. So the expression is 4 pi n a cube c square e to the power minus b c square dc. Okay, so dnc is the number of molecules which have their velocities lying between c and c plus dc, and this is the expression for the dnc, number of molecules.